this thing have a timer on it?
No, I can, this does.
Oh, that does, okay.
Yeah. All right, yeah, so good afternoon. Appreciate everyone's patience working through the combo of a hybrid and in-person event. This meeting is being recorded. We are going to start with our first speaker, Michael Marcus from Northeastern University, and I will let you take it away.
Great. So I sit down where you are, or where?
If you wanted to, I think they can hear you from any spot, and you just let me know when you want me to change spots.
Okay.
Yeah.
I'm glad. Is someone seeing me, or no?
Yeah, can we get, no, there is not. Actually, if you wanted to sit here, and that would be easier.
Nobody seeing me. What do I hear?
Okay.
Great. I'm glad to give this presentation today. I'm a spectrum walk by training, or at least by experience. I used to work for the FCC for a long time. And if you need spectrum above 100 gigahertz, which seems to be implied in 6G, but people can't seem to agree upon, it turns out spectrum sharing is an important issue. Next. And let me point out, as one who is both a techie and a spectrum walk, on the right we have good old Maxwell's equations. I prefer differential form, but you can prefer the integral if you want. On the left we have symbol of spectrum policy. In this case, International Telecommunications Radio Regulations, which are a treaty obligation in general of all the 193 countries that are members of the ITU. And both of them come together when you're designing exotic new technologies that set precedents. And you've got to pay attention to both of them, and their impacts be just as real. Next. So what's special about above 100 gigahertz? It's the next frontier of spectrum technology, but it's also different because the reason you want to go there isn't that you want to have a 3-digit number for your tuning frequency. The reason you want to go there is if you want greater than 10 gigahertz contiguous spectrum for some application. If you don't need greater than 10 gigahertz, it's a hell of a lot easier and cheaper for everyone involved for you to stay below 100 gigahertz. So please do not go above 100 gigahertz just because you want to have 3-digit tuning numbers. Greater than above 10 gigahertz conceptually could enable radio links of a terabit per second with low latency and high volumes for fixed and mobile links. Is there a need for mobile links? I don't have the slightest idea. Some people think there is, some people think there isn't. I think it's pretty clear there's a need for fixed links, at least for backhaul. But there are these unique sharing issues. The physics is also different. Atmospheric absorption is a key issue in propagation. By atmospheric absorption, why does a cup of water heat up in a microwave oven? RF energy is absorbed. Similarly, in various frequencies above 100 gigahertz, either oxygen or water absorbs RF energy. It doesn't heat up the air, but it does decrease the power significantly more than at much lower frequencies. The small wavelengths involved allow different types of antennas that are used at lower frequencies to create some interesting opportunities to facilitate sharing. But we have to remember that all antennas have side lobes, and designers can move side lobes to where they're least harmful. Next. Okay, so here are the things you can do. You conceptually could have fiber optic-like connectivity using greater than 100 gigahertz and very low latency, but fiber optics is really, really cheap in hardware cost. However, depending where you are, fiber optics is either cheap in installation costs or amazingly expensive in installation costs. The numbers of greater than $1 million a mile come to mind in urban areas if you don't have existing ductwork in the ground. Also, fiber optics has a problem. It has longer installation time. So if there's a news-breaking event where you have to get a lot of connectivity fast, fiber optics may not do it. Terahertz technology, therefore, may be advantageous for temporary installations, emergency service restoration. So in essence, the day after the big earthquake, as California drifts off towards Hawaii, if we want to talk to people in California, we might want to use terahertz technology to connect them until they get beyond the horizon. Also, locations where fiber optics is time-consuming or expensive. There is a non-communication technology for short-range testing in the order of centimeter range, called Terahertz time domain spectroscopy. It has some similar questions, but this is a telecom meeting, so we won't go much into that. Next. Okay, this is where the sharing problem comes from. This is the famous US spectrum table. I happen to hate it in this format, but okay. A lot of people are used to it. This shows the part of the spectrum from 100 to 122 gigahertz. It's similar moving up, not quite as bad. The ovals in purple on the table show you the bands that are passive. Basically, virtually every band in this particular piece has some passive use, some of which is more highly protected than other passive use. That book from National Academy of Sciences, I give you the URL, has some reference. In many of these bands, the protection of the passive technology is absolute. Now, radio astronomy, you might think is a problem. It really isn't, because in radio astronomy, above 100 gigahertz in almost all cases is in remote arid locations. Think of northern Chile. The one case in the US which is even marginal is a mountain outside of Tucson. No place else in the US other than Tucson area is there radio astronomy with commission. But these Earth exploration satellites are basically passive weather environmental satellites in NGSO orbits that are looking down, and they could very easily get interference unintentionally. Next. Indeed, the ITU's radio regulations contain 10 prohibited bands in 100 to 275, and to compare this with VHF and UHF, there are protected bands up and down the spectrum, but you can see at VHF, UHF, and even SHF 3 to 30 gigahertz, there are only 4 or less prohibited bands, and the fraction of spectrum tied up to prohibited bands is also a lot less. So there are passive bands, but you've never had to worry about them. If you go above 100 gigahertz, you do have to worry about them. And particularly these 10 bands and listed in 5.340 start off with the cheerful words, all missions are prohibited. This makes sharing difficult. Next. However, most of those bands were put in at the year 2000 World Radio Conference. And when that was done, there was concern about whether this absolute protection was really necessary and whether sharing might be possible. So at this conference, there was a provision called Resolution 731, which allows for sharing under certain circumstances. Next. And this is Resolution 731. There's the URL where it comes from. It shows that while you must protect passive systems, there is a limit to how much you have to protect them. It is referenced in here. There's a quantitative limit, which I'll show you in a minute. This deals with sharing from 71 to 275. Above 275, things are not as complicated, but there are some also problems above 275 gigahertz. It also says the burden of sharing should be shared as much as practical. I'll get into that in a minute. But both passive and active services should try to share with each other. So there is a framework for sharing that was adopted in the year 2000, and we'll get it. Next. It does link to an ITUR document which gives sharing limits. These are power at the passive satellite NGSO orbit, oddly defined at the terminals of the antenna, not the RF field in front of it, at the terminals of the antenna. But there are numbers here, so you have a goal of how much power you can expose the satellite to by accident. Next. Okay. This is my favorite chart. It came out of our discussions at Northeastern University. The gray vertical bands are the bands in 5.340 where transmissions are absolutely prohibited unless you can show that you meet the previous limits. The curves in here are the propagation curves, and what's not only is absorption key, it turns out propagation critically depends on elevation angle. So horizontal paths, which in general is what telecom is interested in, most telecom systems don't go 45 degrees up in the air, actually have an amazingly high attenuation. And if you deal much in dBs, you may realize you've never seen a dB number greater than 1,000. Most dB numbers are 2 digits. So this is weird stuff. The red numbers are bands that you might be able to use if you can show each of those red lines crosses one gray bar, which means they share with one passive band. So it conceptually is possible to get 48 gigahertz contiguous spectrum between roughly 120 to 160 if you could share with band in 150. Which it turns out, while it's heavily used today for weather satellites, may not be much use in the future. But this shows how much spectrum you can open up if you could figure a way to share with passive spectrum. Next. I briefly will mention the terahertz time domain spectroscopy, not a communication system, but it's essentially an ultra-wideband technology. Ultra-wideband on steroids because it has bandwidth of like 100 gigahertz, much. But it is used for both civil and military uses, often to measure surface parameters. And in the space shuttle program, it was used after the disaster to verify that the shuttle tiles were actually glued properly to it. But it has the same sharing problems. Those in the lower right, there's a picture of the spectrum of this. Showing how it typically covers a gigahertz of spectrum. Next. It is in commercial production. So for sharing with fixed service is spectrum talk for point-to-point microwave. There are a variety of ways you could share. One is by greater than normal suppression of high elevation angle side lobes. The only way the satellites can get interference is from side lobes, not from the main beam, because the main beam gets lost in the absorption. Typical commercial antennas generally have side lobe suppression of minus 25 dpi range. That's all you need. You can do better. It's just not needed. Could be another. Another method is keeping track related to the passive satellites while you're standing somewhere on Earth, appear on the horizon, rise in the horizon, and disappear in the other direction. They have a known azimuth and elevation. Indeed, these satellites have published orbits. If you built your terrestrial network as a mesh network with dynamic routing, conceptually you could reroute the signals in your terrestrial network as you calculate the side lobes that illuminate the satellite and avoid that there. Another way to do it is to put a null on the satellite as it passes over. Next. And you want to know how you reduce side lobes? Those are two examples of technologies with much lower side lobes than normal commercial antennas, large radio telescopes, and AWACS-like aircraft. So this is no big secret. Next. Tracking a null is straightforward. It could be done with a MIMO-like antenna, but with a different control system than MIMO antennas. But in this case, you know what the orbit position is, so you know that. Next. Here's a picture of a mesh network. The NORAD database, TLE database, will tell you where the satellites are, compute the exposure from each of the paths, or pick the paths that have minimum exposure. Next. One problem is, what if you have 15 satellites visible in the sky at the same time? We may have to get with our friends at NASA and say, let's pick the orbit so there aren't tons of satellites visible at a time. Radio Resolution 731 says we should equitably share the burden going in certain orbits, or there's an example of a present set of satellites called the A-Train, which actually flying in formation. That would simplify the thing too, but that's only used for one frequency at the moment. Next. And here's how you can get involved if you're interested. Points of contact in the U.S. to get involved in ITR who's discussing these things. Next. And so you can share. It's challenging. If you want more than 12.5 gigahertz contiguous spectrum, you have to find a way to share. So I will stop right there and